Welcome to my talk about event-driven microservices. Great to see that you have joined in such large numbers. So, a little bit about me. My name is Urs Peter. I'm so-called senior software engineer because I have a lot of gray hair and I'm walking around this industry for already quite long. During my daily life, I really am with my fingers in the mud, building systems as a solution architect or lead engineer. Besides that, I'm also a trainer at the CQRS Academy, where I developed a variety of courses, like the ones here, Event-Driven Architectures, but also language courses about Kotlin, Scala, also a certified Kotlin trainer. I will not present this presentation totally on my own. Jens will join me. Who is Jens? Jens is a virtual CEO, and because of lack of technical knowledge, he's the one who's asking the stupid questions, which of course, in general, tend to be quite valuable. So in that sense, he will challenge the things I'm saying today. Say hi, Jens. Okay, so I would like to know a little bit more about you. So who of you has to deal with or is burdened with a microservice architecture? Please raise your hand. Okay, not that many. I would have expected a little bit more, but that's fine. Who of you is happy with the current state of your microservice architectures of the ones who are using it? It depends. It depends. Okay. That's an answer which is never wrong. It depends. Who of you is unhappy with the current state of microservice architecture? One. Okay, that's not too, it's not really that much. To be honest, I would have expected more, but we'll see. Maybe the depends can be turned into different ways. So, in order to understand why the things are the way they are in the present, it helps to understand the past. Because the shortcomings of the past shape the future solutions, if the past doesn't repeat itself, right? And this is particularly true for system architectures too. So the styles we had since about the 60s were monoliths. That's the only way we could build applications. Why? Because we had these mainframe machines, huge computers, and everything that needed to happen from a computational point of view needed to happen on this particular machine. So monolith was the most straightforward choice. Later on, about in 2000, we got service-oriented architectures. You might have heard of these. And eventually, since 10 years, we are burdened with microservices. So the question is, why do we not still build monoliths? Apparently, there's something wrong with monoliths, right? The point is, when you start out with monoliths, everything still looks quite fine and well. Why? Because reason is quite simple. You have a simple code base that interacts most probably with a database. That's all you have to care about. Consistency is really not a big concern because it's a database. You have strong consistency guarantees. It's very reliable. As long as this database is running and your application server, everything is fine and dandy. And this is, I think, for a big part due to the fact that you have a minimal amount of distributed computing you have to take care of. Okay, so when you keep the monolith in this size, I think everything is fine. Businesses grow, monoliths grow, and the more it grows, the less happier the faces start to look like until you reach this point where things get quite bad. In the sense that it's this huge tangled code base nobody understands anymore, which is hard to scale because normally the bottleneck is the database, and scaling a database, especially on the on-premise area, is quite a big thing. It's expensive. When multiple teams work on the same monolith, extending it and maintaining it is also a nightmare, which is also true for deployment, because somehow you need to make sure that you reach a consistent whole. In order to reach that, you need a lot of coordination between different teams working with this monolith, a lot of management, and so on. So once you reach this bud of mole, this spaghetti stage of your monolith, it's time to run. And this is not only true for the technical aspects of the system, it's also true for the business aspects, in the sense that time to market becomes an issue. It's a very expensive system. market opportunities are lost, and last but definitely not least, developers that are burdened with a monolith normally tend to be not the most happiest species on the planet. Well, these problems, they were kind of realized, so they came up with our next style, which were service-oriented architectures. And this was actually the first effort to partition these pieces into more manageable subparts. I think that was more or less what this was all about. So what you see here, so you had this huge thing which now decomposition into smaller parts. Of course, these smaller parts, they had to interact with one another. And in the service-oriented area, this was the infamous service bus, which all communication went through. And this kind of led to, well, smaller parts, and smaller parts are most probably easier to understand. Same is true for these aspects, so maintainability, deployment, and so on was easier because it was smaller, more manageable. Well, these are the benefits, but you also had to pay a price to get there because, first of all, this service bus was a big issue from various perspectives. Scaling is an issue, configuration management issue. Normally it was one team that managed this service bus and they had a backlog till here and you were at the bottom of the backlog. The same is true that all of a sudden you had to do more distributed computing, not to mention the web service standards, which of course are awful. So in the end, reliability and availability all of a sudden became an issue, which wasn't the case before. And also scaling was still an issue because most of the time these services used the same database, and scaling this database was again a costly endeavor, especially when it was on premise. Okay. So then eventually we got microservices. So what are microservices about? Actually, microservices, they should have learned from the shortcomings of service-oriented architectures, kept the good ideas, of course, but then re-architected their purpose to fit modern infrastructure like cloud, containers, serverless, NoSQL databases, which then eventually turns out to, if you do it well, architectures that look like this, but more on that in a minute. So the question is, what does make a microservice? Or what does a good microservice make a good microservice? And one way to explain that is to focus at the design principles you should actually follow in case you want to have this microservice landscape that really works and doesn't do the opposite. So let's look at the key principles you should design microservices on. The first one is isolation. Well, what does isolation bring us? A lot. It allows us to scale individual parts of your system. If one part fails and you have true isolation in place, then you also automatically get resilience. So one failure of a system won't affect the whole, which in a monolithic application, of course, is a big issue. If one part there blows, then most probably the whole thing blows. You also get continuous delivery because you can deliver these individual parts on their own, and the same is true for independent development. So also there you can scale development much better than you could with the monolithic area. Closely related to isolation is autonomy. What does autonomy mean? It means that a system has access to all the data it requires to fulfill its task. And another side effect of that is that it is able to publish its own API. I think the most troublesome aspect of the word microservice is the micro in the service, because it emphasizes the size. Definitely size matters, but actually much more important is that you think more in terms of responsibilities. A microservice should have a single responsibility. Domain-driven design can help you with that. You might have heard of this term. Can have these event storming sessions that allow you to deduce bounded context, as it's called, and normally a bounded context could be converted into a microservice. That's a different topic. I could give another presentation only about that. We're not going to go too deep into that. In the end, we want to have a service that has a single responsibilities, and definitely size is somehow in the single responsibility, because if you have a monolith, you probably don't have a single responsibility. So size is somehow related to single. And heuristics I use is that a microservice should more or less fit in one person's head, more or less. Should be developed with at most one team, and it shouldn't take more than weeks or months to develop. If you violate one of these, you probably have to scratch your head whether this single responsibility principle has been regarded. Another interesting design principle, which actually is a consequence of isolation and autonomy, is exclusive state. So whenever you want the microservice to change its state, the only way you should do that is via its API. So if you have multiple microservices using the same schema, you definitely violated this principle. And of course, violation is not such an issue if it wouldn't have consequences, but this definitely will have consequences. The one that is probably most overlooked is that the default communication pattern between your microservices should be asynchronous message passing. Asynchronous message passing. Why? Because it gives you a lot of these capabilities, non-functional ones. And in the rest of the presentation, we will focus for a big part on these ones. And the last one, which in my experience is not often a big issue because modern infrastructure just offers you that, like Kubernetes, is location transparency, which allows you to address a certain service in a virtual way. So instead of having a hard IP, as an example, you use a DNS, and then DNS figures out to which healthy instance your request is routed. Okay, with these principles in front of us, let's design a microservice architecture that all honors these principles. If we add in Jens. Okay, Hans apparently has already a blueprint from his architecture department, and he would like us to have a look at it. Let's do it. So what did they do? They created 3 microservices for our order process. They all have the individual databases. So let's follow the flow. You submit the order to the order service. Then you fetch some data from the CRM service. Well, I need data of my customer, so that's what I have to do. Eventually, I do a call to my inventory service, which will ship out the order and update order service so that I know the latest state of my order. Okay? So I think that's a valid question. What is wrong with that design? Because it's quite straightforward, right? If you don't think too much, that's probably where you end up as a first trial. Well, in order to see what's wrong with the design, let's challenge it. First of all, what happens if one of the services is not available? Say if the CRM service has a maintenance window or has some issues. What happens then? Well, I can't process orders anymore. Kind of issue, right? Of course, you can mitigate that. You could make the CRM service high available, but that's costly. Or I could implement some retry mechanism, which adds complexity. Not to mention about user interaction I have to deal with. So what you actually gain with synchronous communication patterns is tight coupling. And tight coupling, in this particular example, has a lot of unpleasant side effects. So in this particular case, we definitely get a non-reliable and a non-available system. Let's see how this type of design, what kind of control flow it favors. So who is in charge of the process? Most of the time, it's often a single service. And this service then depends on all the others, like here the order service. Who's in control of the state? That's actually the pattern we've seen before, where every microservice handles its states exclusively. So that's kind of fine. In other words, if we approach our microservice architecture that way, what we get is a centralized control flow, which has Definitely the side effect that complexity and dependencies are concentrated on one spot, and because it's on one spot, the chances are also high that availability and reliability is impacted. The more dependencies you get, the more likely the chance is that one of these dependencies doesn't work and your flow fails. And this is what I hear companies tell me what they encounter. Last but definitely least, how does our landscape evolve? So the more microservice I add to my landscape, what is the result I get? So let's assume we add an analytics service that needs data of all these services. We have two ways to get the data there. We could either adjust all the microservices to push data to this analytics service, or we could make the analytics service fetch data from these various microservices. The point is, coupling is only increased. And therefore also complexity. So all the microservices have to all of a sudden also make a call to this analytics service, increase complexity, or you get all of a sudden unexpected load because this analytics service kind of pulls a lot of data out of your service. Your service doesn't have yet auto-scaling in place, and there goes the reliability of your order service. So what we see is when you approach microservices in this particular way, you get an interdependent evolution model, meaning that the more units you add, the more complexity and coupling you create. And over time, these non-functional aspects will definitely slightly decrease, and your headache will increase. So, by the way, why did we start out with microservices? Oh yeah, we had these problems with our monolith, right? We wanted to solve. That's what we actually wanted to achieve. But as we've seen, we still have these problems. In a monolith, we still had some benefits, right? Like consistency, reliability, not a lot of distributed computing. But also these benefits are gone because we have to deal with a lot of distributed computing. Things are eventually consistent or even inconsistent. It's getting unreliable. So the little spaghetti monster we had on the left turned out to be a legion of big, large, ugly spaghetti monsters. And I know this is a very ugly slide, but that's actually also the whole point here. When you address your microservices in that way, this is what you end up with. Who recognizes this? Maybe it's a bit exaggerated now because we need to set the point straight here. So who recognizes this this problem? One, okay. I see some of you, quite a few then holding up their hands. Cool. So we are more or less on the same page. Okay. So what went wrong? And again, these principles help us to figure out what did we overlook. Let's assume that this responsibility thing wasn't a big issue. Of course, the more fine-grained merge services you make, they just execute a single task, the more remote calls you get, the more likely it is that one of these calls will fail. But let's assume for our case, they kind of made this right. Inventory, order, CRM kind of feels like a bounded context. Location transparency also is not an issue, as said. Infrastructure normally takes care of that, and in my experience, that just works. So when I deploy a new container, this is just all done by my Kubernetes, and it works. Let's also assume that exclusive state principle we have honored in the sense that every microservice has its own database and exclusive access to it. So apparently, it's more on the left side, right? So isolation is an issue. Why? Because we have tight coupling. And whenever you have tight coupling, your isolation is gone. The same is true for autonomy. For instance, the order service has these dependencies to the order service to fill its task, so it's not autonomous anymore from a runtime perspective. And of course, asynchronous message passing. This architecture has never heard of something asynchronous. And if we try to kind of figure out the root cause, is that tight coupling between services is our problem. Tight coupling is not a problem by definition. Think of it. If you have a microservice and a database, they're tightly coupled, but that's fine because tight coupling allows you to derive a lot of value out of your components. They also evolve together, right? The Skiva evolution and your microservice, they evolve together. It's under control of one team, and so on and so on. So tight coupling is exactly what we want in this context. But tight coupling across microservices That's where the problems start. So, I think Jens has a valid point here. Can we fix this? Do we have alternatives? That's a valuable quote, which is said to come from Mr. Einstein, but of course these are things you never really can evaluate, so I left it out. But nevertheless, it's a good quote. It means that the problem we created with certain mechanisms, if you try to use the same mechanisms to solve the problem they introduced, we're probably not going to succeed. So we have to address this problem from a different angle. And of course, this presentation is about event-driven, so most probably we are talking about events here. So it's time to introduce Mr. Event. What is an event? Well, it's actually something quite simple. It's a fact that has happened. And that's nicely depicted in the way you name events. We have here the order placed event. So order refers to a noun, the thing. And the second part, placed, depicts the change this thing has undergone, order placed. So what does an event reflect? It reflects the state of the world. It simply tells you the way the world is right now. So it's not a state of mind, a thing we want to happen. No, it's just what has happened. Does it have intent? No, it just tells you this is how the world is. Processing is, by definition, asynchronously. And does it expect a reply? No, it does not expect a reply. Of course, new events or new actions can be taken upon reception of an event, but by definition, event by itself does not expect to happen something else. Just tells the world, this is the new state, good luck with it. Events come with two capabilities, and from a really high-level perspective, these are the ones that will give you new power to address the problems we just introduced. The first capability is that it can serve as a notification. Right? So the order is shipped, and when order is shipped, then ... something else can happen. When I ship an order, I also bring in an invoice. So there's also some data involved with it. In that sense, I also can use an event as a data replicator. So let's see how these two capabilities could be placed into our architecture and suffer these shortcomings to see how this could be used, right? Well, before we can actually see the impact of it, most probably you will have to introduce something like messaging middleware, like Kafka, for instance, or any other messaging system, which, by the way, is not really necessary. I've built microservice architectures without messaging middleware in a perfectly event-driven way. But that's actually a topic of a different talk. Actually, quite elegant solution I'm still happy with. But I think more mainstream, you would have to choose for a Kafka or something like that. Reliable message bus that can handle a lot of load. Okay, once we have this in place, instead of the order service to call the inventor service, it simply emits order placed, and that's it. The inventor service then picks up this event, realize, hey, I have to ship my order, so this is the action that takes place based on this event. Once it has been shipped, it emits another event, order shipped, and eventually the order service consumes this event and does the processing it wants to do. So we quite nicely cut out the dependency between the two from a runtime perspective. This is what you get when you use events as notifications. The question, of course, is how can we handle this query relationship in an event-driven way? Right? We need the data at the time we get this order. So how can I get the data but not have this synchronous coupling to another service? Well, this is when you use events as data replicators. So whenever the CRM service gets a change on a user, it emits events. Customer registered, changed, deleted. The order service consumes these events and creates a local view of the data it cares about. So it doesn't replicate the whole CRM system. No, it simply creates a local view of the data that is relevant for this order service to fulfill its task. So whenever an order is submitted, I simply do a lookup of the customer in my database, because I also do a lot of other lookups in my database for the order processing, and everything is fine. So the question is, yeah, why is that better? Let's see. Let's challenge this design. So what happens if one of the systems is not available? Say the CRM service is not available. Well, not much happened, right? Because I have my local replica. I simply can continue processing the stuff I was processing with. The nice thing about this approach is also that the CRM service doesn't have to be a highly scaled system, because the order service fetches so many timed users. It could be quite a simple, small system. Could even be an old monolith. As long as it emits events and allows me to create a replica of the view of the data I care about, everything is fine. So what we see is that when we use an event-driven approach, we get loosely coupling, and therefore also isolation and autonomy. And this is good for our availability, because we can cut out these synchronous communication links. Let's look at how our control flow is looking like. In this particular example, and we see that you can vary in that, but for now, let's just keep it purely event-driven. Every microservice fulfills a portion of the processing of the whole chain. And the flow of events actually depicts our flow. Right? So what you see in the middle is actually what is happening from a business perspective. And microservices just interact with that, but it's not the system itself that is actually relevant, it's the flow of events that is relevant. So what we get is a decentralized and collaborative control flow. This, of course, has advantages. Complexity is spread evenly, so that you get a concentration on one spot is not very likely. And because we're so loosely coupled, our system is extremely reliable. Then finally, let's see what happens if our landscape starts to grow, if new services are added. Our famous analytics service is added to the mix. What is the impact for the other microservices? Well, there's not much impact. It simply consumes the events that are already there, builds its own view out of it, and we are fine. So what we get, instead of an interdependent evolution model, we get an independent evolution model. So also on this level, isolation is guaranteed. So new services do not lead to new complexity and new coupling. So from a very high-level perspective, this is more or less what event-driven can do for you. It helps, of course, if you get more tangible patterns to implement some of these use cases. And the good news is, of course, we have some patterns out there. So let's look at them. And for now, because we have limited time, we look at the top 3 of the patterns I use in my professional life, which can really resolve a tremendous amount of the problems we had in the beginnings. So I call them the true musketeers that will save your microservice architecture in trouble. Let's start out with CQRS. Before we look at CQRS, however, let's do one step back. And one more time, get very clearly pictured the challenges you have with a microservice architecture. One of the key challenges we have is that you have to deal with decentralized data management. Right? You have these multiple microservices, they all own a portion of the data. And the point is, data dependencies, if you like it or not, are hard. When you need to process a thing and you need data from various other things, you need data from various other things, if you like it or not. So we've seen that if you try to grab all the data at the time you need to process it from all the other services at the time you need it, we get in trouble, right? We've seen the drawbacks of that. So how could we do this differently? Well, we could inverse the whole thing. So instead of grabbing data at the time I need it, I make sure that the data flows to me so that whenever I need to do the processing, it's already there. That's probably the biggest mind shift you have to make in order to get the value out of your microservice architecture you actually expect it to. And CQRS is, in that sense, a formalized approach to achieve that. What is CQRS? In a traditional system, you have a domain model. I think everybody knows what a domain model is. Relational or just in an application or domain model. And this domain model needs to fulfill two purposes. It needs to fulfill all the write aspects, depicted here with commands. So commands actually something that wants to perform a change in your system, which normally leads to some mutated data. But it also has to satisfy your read needs, in the sense that you have queries and then you get all these joins and then it all of a sudden doesn't perform anymore. Probably we all have encountered this problem. And that's because we rely on one domain model. CQRS does actually quite simple, as it's called, segregation. It says, hey, instead of having one model, let's have two. We have a model for our writes, so for the commands, and we have a model for our reads. Of course, the read model is deduced from the write model, but it can look quite different, optimized for the read needs. And it can even be in a different database. So you could have your domain model in a relational database and your read model in an Elasticsearch because you want to have rich text search. So all the writes would then go through the write model, all the reads through the read model. CQRS gets really interesting when you do it across microservices. So here, our analytics service consumes events from CRM, building its local view, a bit like we've seen before. And it starts getting really interesting when you start consuming events from all the other microservices. So you can create aggregated views of all the data that is around you to fulfill your particular purpose. What I've come to realize in my consultancy work is that replicating data feels for many people counterintuitive. I don't know why. It's maybe of the SOA area where they say everything has to be reused, reuse of services, replicating data, then we have data there and there. As said, data dependencies are hard. You anyway need the data at a certain point in processing time where it needs to be. If you fetch it runtime, or it's already there. So once you start embracing data replication, you will really have an eye-opener. I guarantee you that. So it helps in the beginnings to repeat this for you as a mantra. It's good, because I assure you, you will get happy faces once you step over the threshold. And it took me sometimes really a lot of effort to persuade some sort of all the architects that this is a good thing. But hold on, it will pay off, really. Okay, the next pattern is closely related to something you will encounter when you deal with multiple resources like a database and message bus, which is actually consistency. And we definitely want to have our architecture to be fully consistent. So you have to deal with something that is related to distributed consistency. Well, Jens, apparently he was also a developer in his young days, and he remembers when you had this database and you had a queue, then you had to have something like a two-phase commit, distributed transaction to ensure that either the whole is committed to the queue and the database or nothing at all. I think maybe all the guys among us also remember this area. Yeah. So, say you don't do that. Right? So you simply commit a transaction database, and unfortunately I still see this happening in many projects. You commit something in domain model, and then you emit your event on a queue, and if one of these things fail, then, oh, we're in trouble. And especially when you have a larger microservice architecture, figuring out where the inconsistency started out, that's really an evil thing I don't want anyone to do on his daily job. So really need to make sure that we are consistent. So anti-pattern. If you have this in your code, I really urge you tomorrow, change that. Well, how can you change that? Yeah, we could of course have this two-phase commit, right? Jens still remembers from his old days. And the question is this a good idea? Well, most modern NoSQL databases, as well as modern messaging middleware like Kafka, they do not support that. So maybe you want this, but it's not there. And also, if it was there, in general, it's not such a good idea, because these distributed transactions decrease your performance. They're quite heavyweight. They're not always working the way they should. At least that's what I've seen many times. All of a sudden, still things get corrupt, even though they shouldn't. Or things really start to crash. And because a two-phase commit requires two resources to be available at the same time, it's also not that good for your availability, right? Even though a message system and a database, we kind of hope that they're there, but still they're required to have them there at the same time. So how can we solve that? The solution is actually quite simple. So what we do is we introduce something which is called an outbox table. And whenever we submit a domain change in our domain model and an event, we commit this in the same transaction. And the event will be stored in the outbox table, and the rest will be stored in our domain model. Okay? Then you have this thing called polling publisher, which polls the outbox table and takes out the events it hasn't seen yet and puts them on the messaging middleware. Problem solved? Well, we still have a database and a message system here, right? So somewhere in the outbox table, we need to flag that this event has been pushed on the messaging middleware. So we still have two resources. But the good news is that's not really a problem as long as you keep at least once delivery semantics. At least once delivery semantics imply that an event can arrive multiple times. And when you start designing your system with these semantics, which isn't that hard, it's for instance just checking that you have had a certain order ID already, or an ID that is related to this event, then everything is fine. Yes, time is running. Okay, so this was consistency insurance within a microservice. But there is also something like consistency over microservices, across microservices, especially from a business perspective. And this is where the last powerful pattern comes in, which is the Saga, which is something between consistency and coordination. So what is a Saga? Say the inventory service realizes, hey, my inventory is depleted, I cannot deliver the order. Then we go into an alternative flow. What needs to happen from a business perspective here is that we need to initiate a refund, and we need to inform the user that the order won't be delivered, right? And the Saga actually does exactly that. Saga comes with, as it's called, compensating actions to make sure that from a business perspective, everything is consistent again. So in other words, a coordinated series of local transactions, this is what a Saga does. It's important to realize that local transactions are all atomic, like we've seen, for instance, with the outbox table. This is just a single database anchor, which is strongly consistent, but the Saga as a whole is not. So how can the Saga ensure that the whole is consistent? Well, you need to write code for that. So there's no magic solution of super transaction manager that keeps everything consistent. No, you need to simply write code for that, test it, that it works. Which you have to do anyway if, for instance, you interface with an external service. There you cannot even have strong consistency on a database level because it's a total call to outside of your company. So then it's kind of evident that you have to solve this with code. There are two flavors of Sagas. One we've actually already seen, which is the choreographed Saga. So say in our inventory service, something goes wrong. What this inventory service could do is simply emit another event, say, order failed. Then the payment service could pick that up and say, oh yeah, the order failed, so oh yeah, then I have to refund. Okay, I do the refund, and I say, order refunded. And then the order service could react on that too. This is one approach to address it. It has advantages in the sense that it's still perfectly loosely coupled with all the benefits thereof. But this approach also comes with downsides. What we see is that every microservice fulfills a portion of the whole flow. And the more complex your flow gets, the harder it gets to reason about what is actually happening. Rules are spread across different systems. Every system needs to keep a certain state of the order. So the state is replicated maybe in a way you don't want. And it's also kind of hard to track the current state of order. So which system tells you what's the last state of an order? So these are disadvantages you get with a purely choreographed flow. Fortunately, there is an alternative to that. So if you have a simple flow, I think choreographed flow, as said, is the most stable, but maybe from a maintainability point of view, the harder one. A counterpart would be orchestrated sagas. And in orchestrated Saga scenario, you have a Saga coordinator. That's a single unit that actually takes care of this consistency in a persistent way. So the Saga coordinator keeps a log of all the things that have happened. And whenever something happens, then we got some notifications here. Whenever something happens, the Saga coordinator then reacts with events or commands, doesn't matter, as long as they're asynchronous, that things stay stable. As said, reasoning is getting easier with a coordinated Saga. Also, business logic can be changed in one spot, as long as this Saga doesn't have to interact with many other things, but slight changes can be done on one spot. And most of the time, other services also become simple because they do not need to have all the state to know what kind of action they have to take. So this is really a kind of yin-yang question you have to solve which one you want to choose, but you have the two. And the sad disadvantage is that maybe too much complexity is put again into one place. So, should your microservice architecture be in trouble, I hope you remember the TEQnation 2022 event to embrace your events. Call in these three musketeers, and should you have applied them, then you definitely can tick the boxes on the design principles. And of course, that's not a goal by itself, but you will see that your microservice architecture will eventually thrive and pay off, not only for you as a technician, but also for the business, which you shouldn't forget as technicians. Okay, thank you.